Dear student, colleagues, and all the viewers who are watching this program live from Facebook page Physics Adda, I would like to invite you in our international physics webinar. And I'm happy to share with you that today it is our 31st physics webinar. Good evening to all here in Bangladesh and good morning to all those who are watching from USA. Hope you are well and safe from Corona pandemic. And we are actually, we know we are passing a very bad time. We are living in a Corona pandemic situation. We can't continue our normal academic program. So we have to start our online program. Our Department of Physics, Pabna University of Science and Technology, have started some online program like online classes and online physics webinar. And we have actually invited a lot of physicists from different countries, and I'm happy to share with you that today it is our 31st physics webinar, and in those webinars, you are pleased to know that the physicists from different countries are coming as a main speaker, and they share their knowledge with us, and they delivered their speech, and by this way, I think students are benefited. So in that continuity, today we have with us Thad Robert, theoretical physicist, a private think tank, Utah, and former astrophysicist, geoastrophysicist, flight lead at NASA Johnson Space Center, Houston, Texas, USA, joining us from USA online. So he have already connected with us, and I'd like to welcome our speaker. So good morning, sir.
Good morning. Thank you very much for having me.
Yeah, it's our pleasure, sir. And good morning and good evening in Bangladesh. And I'd like to welcome in our webinar and in my Bangladesh and our university too. And it's our pleasure to host you in our international physics webinar.
Thank you.
So right. You can start your session. So okay. I think a student will benefited by your lecture, and we have a discussion session at the end. So anybody can join with us, and student can or anybody can ask question by commenting. So thanks again, and I would like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology. So thank you. You can start your session.
All right. Well, let's switch to this screen here. So I have an exciting topic. Hopefully this is, I'm not exactly sure what the breadth of my audience is here. So I'm going to start out more general, and maybe you could let me know if I should
I can.
Let it go. Yeah. All right. So I titled the talk "The Mysteries of Physics," and I mean this to be a general introduction, but specific to the remaining mysteries that physicists haven't been able to decode or figure out. Right, the inputs that we had to put at the base of our assumptions that we measure, but we don't have an explanation for. So these are the open questions, right? And this is the structure of the talk here. So we're going to talk about first, well, sorry, the structure is going to be this one, the next slide. So we're starting from today's ontology, the picture that we tell in physics, the best picture we have. There's a little bit of a gray area there, but we're going to go with quantum field theory as the best picture. And this quantum field theory starts with a structure. So we have a space-time where we have our dimensions already assumed. We have photons that are imported, all the constants in nature that are imported from observational measurements, right, to put in our equations. We have an entire particle zoo. So we have this whole list of fundamental particles that all have their own mass, charge, and spins. Okay. We have dark matter and dark energy, which are kind of left field, unexpected, new additions to physics, really, and a Big Bang event. So quantum field theory also assumes the structure that gives us all the four forces, the effects of general relativity, quantum mechanics, and the wave function. But those are all still assumptions in it. Now, once we have this structure, once we have all these assumptions in our model, the way that quantum field theory is set up in a very natural kind of fluid dynamic way, it takes those assumptions and builds our world very fantastically. So this is a fantastic story that we put together, but I want to make sure that we're clear for all physicists, because it's really exciting to be in this topic. We haven't answered everything clearly, right? We don't have a picture that gives us a full satisfactory answer to all the quirks and anomalies we found in nature. The regular structure even we found in nature can't be yet explained, and so we're still after that. That's right. This talk is then going to be parsed into two sections that are going to kind of repeat each other. The first section, I want to go over all these actual unexplained elements. So the constants of nature And then we're going to focus on the fine structure constant. And then we're going to talk about the charge pattern. I'm sure this is all familiar, but I want the actual specifics to be fresh in your mind before we go from after this. The mass pattern, and then maybe some of the viewers here are unaware of the Coyote equation. It's a little less talked about among physicists, especially if you just go through for masters or a regular tradition and don't specialize in this direction. So we'll talk about that pattern and discuss whether or not it's useful or interesting and insightful. But then we'll move on to part 2, and we're going to work through a model that me and my colleagues have been working on. We're going to start just the 5 elementary boundary conditions it sets up, and then go through all the same structure we just went through and see if it has anything interesting to tell us. So the goal here is always remember to come away with a better picture of reality than we started. That's our goal in physics. Sometimes we don't achieve that specifically, but we try all kinds of interesting ideas. And this one, I think you're going to be very surprised that it's not just an idea at the starting stage where we can kind of vaguely think. This is a specific idea that will actually give us numeric ways, mathematical, geometric ways to derive the conditions we are after and then see if they line up. All right, so starting in part 1, the constants of nature. So for those who haven't spent any time studying the constants of nature, I mean specifically, or in physics we mean specifically, things like the speed of light, Planck's constant, gravitational constant, the fine structure constant. Let's see, I can go like this. There we go, that's better. The elementary charge, Boltzmann constant, magnetic constant, electric constant, Coulomb's constant. I'm sure you've heard of all of these. Engineers, chemists, and so on, right? We're all familiar with these sorts of constants as the constants that scale the equations we use for our descriptions in physics and chemistry and biology and so on. All right, let's take a little bit look at the actual numbers themselves. And this is a step I think that's usually not done because I think it's a natural intuition and a good starting one to look at these numbers and see their units at the end and feel like the numbers themselves cannot carry an important message because, well, it seems like the units are just man-made, right? Meters, seconds, kilograms, coulombs. These are all units that don't feel like natural units, right? However, we're using just 5 dimensions, 5 units, in combination to describe all of these constants. All right. So let's look at the first list again. One thing to pay attention is that we know the accuracy of these measurements are all listed. The error bars here are in parentheses, right? So the last 2 digits have an error of whatever's in the parentheses. So we know these measurements extremely accurate. There's many of them, right? And they need to be accounted for. And if you think that the units they are in are random, it may not be in an attempt you can go after. However, notice that the units they're in are all the same. That is, they reference the same 5 only. So even in that system, a coherent system of units, there must be a pattern that makes sense of these if nature is sensical, and I'm of the camp that it is. So of all those constants, let's back up. Yeah, this one right here. So the 4th one down, the fine structure constant, notice out of all the ones I've mentioned, it's the only one that's dimensionless. So it has no units attached to it, right? It's just a number, like pi. It's a very interesting number. Some famous physicists like Richard Feynman have strongly ushered us to consider it one of the most interesting things to figure out. He feels like it's basically the gateway to the remaining mysteries. So in this list, it does stand out as an interesting, unique number, the only one that's dimensionless. Okay. In fact, here's a Richard Feynman quote. There's a most profound and beautiful question associated with the observed coupling constant E, the amplitude for a real electron to emit or absorb a real photon. It's a simple number that has been experimentally determined to be close to 0.08542455. It's been a mystery ever since it was discovered, more than 50 years ago, and this was in 1985, by the way. And all good theoretical physicists put this number up on their wall and worry about it. Immediately, you would like to know where this number for a coupling comes from. Is it related to pi, or perhaps the base of natural logarithms? Nobody knows. It's one of the greatest damn mysteries of physics. a magic number that comes to us with no understanding by man. I think that's a fantastic quote. And what I really like about this is Feynman's trying to direct us to this mystery. So he's trying to invite us into this mystery. And that's, I think, what we need a little bit more of. We need the entire world to feel more invited into investigating the mysteries of physics, because if we're in a lull, we clearly need more creative sources. We need more creative minds to ask questions that maybe we haven't asked yet. Here, looking at the fine structure constant, by the way, Richard Feynman calls the fine structure constant something slightly different than the one that is traditionally here. They're just the square of each other, okay? So he traditionally notices this is the more fundamental one, the 0.085. If you square that, then you get this. All right, by the way, notice how many digits we have in our measurement here, right? 11 with an error of 24 in the last two. That's an extremely accurate number in physics. So if we get an explanation for this number, it needs to account for that level of accuracy. So that's a really high bar, but that's just what we're at here. All right, charge pattern to remind everybody. So if you arrange the different charges, we notice there's two different groupings. There's charges of 0 and 1 in the fundamental particles, right? Or you can think of those as composite, maybe. And then the fundamental ones below seem to have a negative 1/3 and positive 2/3 combinatorial charge effect. But that's it, simple pattern. This is in many ways geometrically show our pattern this. So that one feels maybe less mysterious, but still we have something to explain there. This one, entirely mysterious, the mass pattern. Here's the number, or numbers. This is the level of accuracy to which we've measured all of these particles, okay? Now I'm putting neutron and a proton on here as still in the fundamental lists. You'll see why, but I mean, if that bothers you, just get rid of the word fundamental and just think, this is the list of particle masses, okay? We know them to extreme accuracy. One little note here, if you're really paying attention to numbers, I hope you are, some of these things are in giga electron volts and some are in mega electron volts. So just multiply by 1,000. Okay, this list right here, the numbers we're looking at here and the symbols we've used to represent these numbers, this represents an extremely fundamental mystery about our reality. These numbers here make up the constituents, and there's 3 more, by the way, 3 more that we don't have measurements for, the neutrinos. So add 3 neutrinos to this with unknown measurements so far for their values, and that lists all the fundamental particles. And this characterizes the things that our world is made up of. In fact, we could say 99% of the baryonic matter in the world that we interact with is mostly just the neutron, proton, electron. But this entire pattern here gives us everything we found so far. All right. One pattern. I was about to say that there's 0 pattern at all, right? No one's ever noticed any pattern in any of these numbers at all, or at least no serious contenders here. But there has been one. The Coyote equation, Yoshiro Coyote, he noticed a while ago that if you take the electron, the muon, and the tau, okay, 3 specific of these particles from this list, and no matter what units you put them in, as long as they're in the same units, you add, well, let's treat the square root of the mass as a fundamental here. And then we're going to add those fundamentals together. So we're going to take the square of the sums of the fundamentals, and we're going to take the sum of the squares. So the sum of the squares divided by the square of the sums. And this is traditionally in fluid mechanics a good way to show like a mixing coefficient. So if you have 3 different actions in a fluid and you were to mix them together, you wanted to know what the squares, or the sum of the squares over the square of the sum, right? Well, this equation, by the way, the Coyote noticed this as an occurrence, but without an explanation for why, okay? So it was a unique thing that might give us a hint, or maybe a geometric explanation of what's going on. What he found was when you put those masses in, you get exactly equal to 2/3 within the error bars of our best measurements. So what's that up? That's 6 significant digits for the lowest of that one, or 5. That's really interesting because the structure of this equation is set up so that if you set it up so that the 3 were completely non-democratic, right? So one of them is completely dwarfing the other 2, a huge number versus 2 small numbers, okay? Then we can treat this basically as a 1 and 2 zeros, over a 1 plus 2 zeros squared. So then we end up getting 1 over 1, or let's call that 3 over 3. But if we go the other way and say, what's the other extreme this equation can support, make it completely democratic, now we go, let's treat them all the same. Pick any number. I'll pick 1. It's easiest. 1 plus 1 plus 1, 3 over square root of 1 plus square root of 1 plus square root of 1, still 3 squared, which ends up being 3 over 9, or 1/3. So this equation has limits of 1/3 to 3/3. Okay, between being completely non-democratic and completely democratic, it can swing between 1/3 and 2/3, and yet in reality, it has landed exactly in the middle. Okay, there was a big sense there for a while, and I think maybe it's died down or it's become less popular, but there might be a clue there to what's really going on. All right, that was the introduction. So let me skip out of here and switch so I can see some faces. Yeah, so I can see your face. I'm going to see. So far, then, what we're saying is that in physics, we've come a long ways to tell a story that we started out with very little details, right? The few things we can see around us and make sense of and so on. Yeah. People had to make stories for them, and notice when you come into contrast a different culture, people had made different stories, right? So then you have to go back to the drawing board and say, what's the truth? Eventually, we develop the full formal field of physics where we have an exact way of going about trying to make sense of the world. We do scientific measurements and proposals, right? However, there's still a big barrier. To make full efficient use of this scientific method, you have to be creatively infusing it with questions to test, right? You can't be sitting and doing nothing. So if you run out of ideas of what else to ask, then you're kind of stuck. You're not doing anything with science. You're stuck at the last best picture you had. So science is set up so that you're never done in a way, right? Like no matter what picture you have, you'll always be trying to ask more questions, which could fundamentally undermine the picture you're currently at, right? In a way, you're kind of self-sabotaging because the goal is not to be right now. The goal is to try to become less wrong over time, right? That's the goal. So it's a very out in the open that we know we're not right because obviously we're not explaining all some of the fundamental things. And until we can do that, we couldn't claim to be right. Still, I don't think we'll ever claim to be right in science because you can never claim you've observed everything, and therefore there's no way you can claim you've imagined how to frame everything that's been observed or is observable. All right, so now I want to go through the same. I hope that was a general. Maybe people haven't been introduced to this concept that way, where they're shown these constants and so on. But I want to go through the research that we've been doing with my team. We start with a slightly different set of assumptions about reality. And if you don't like the assumption, just play along intellectually and say, well, we're going to model a system, okay, that is like this, and see what sort of characters that system ends up having as its natural derivatives, as natural consequences. It doesn't matter whether you think it matches up with reality, except for we're trying to show a match between that model and the actual characteristics in reality. Okay, so there's our goal there, but whatever makes it easier for you to pay attention for everybody. All right, so moving back in. All right, so the first thing I want to introduce in this new model conceptually is our 5 elementary boundary conditions. And in order to make sense of what this means, first you need to visualize what model we're treating. So we're starting with a metric that happens to be quantum fluid, okay? And I need to specifically define everything that means. A quantum fluid, I should say a perfect quantum fluid. So I want this to be idealized, to be as general and symmetric as possible, okay? So we're looking for the simplest description of a quantum fluid possible. In order to be a quantum fluid, you, one, have to be made up of parts. So you have to have discrete parts. In order to be the simplest quantum fluid, we want all those discrete parts to be identical. So every constituent, let's make it a single sphere, the simplest individual constituent, right? And it's elastic. Let's make it perfectly elastic so everything is conserved. That also makes it so there's no friction, no internal viscosity, okay? So this now is the general the fluid, the conception, or the network that we're defining all the available positions in. Okay, so every sphere is a quantum of the fluid, and every sphere represents a fundamental elemental point in the grid that you build to make a map of space if you're going to connect this to our reality. Okay. All right, we need to define then What sort of boundary conditions must therefore exist in this fluid? And how do we do that? Well, we don't have much to go off of, which makes it simple. We have a simple fluid that has to divide internally to make a balancing condition that's self-stable, meaning we need waves to come together somehow. You can have random waves interfering all throughout this fluid everywhere all the time. If a few waves come together just right, so that they twist the fluid itself to wrap back around itself on a closed loop, then we give birth to a persistence, a regular thing that'll continue over and over and over. The minimum condition for meeting this balance in a fluid where you don't already have nearby boundaries to contain your action, right? We don't have a bucket, or don't have man-made boundaries we put in. If we have a fluid and as far out as you can see is just fluid, then in order to get a localized expression of permanence, in fact, in order to get, we should call this really the minimum condition of persistence in the fluid. So in order for any quality at all to persist in this fluid, an action to continue to over and over and over do the same thing, it must find a way to close a loop. Literally, like it won't persist. It can't over and over occur if it doesn't close a loop, if it's not a cycle. So the simplest, of course, way for a closed loop to happen in a fluid is for you to have split hyperbolic division, which means internally you split your rotations, but those splitting, think of a vortex. The stuff coming out of the throat splits this way and this way. We get two directions splitting, but that splitting happens to feed back into the vortex. So you get a stability that comes from internal splitting, okay? And of course you want it to be hyperbolic because it's going to counter your circular. So we got hyperbolic and circular give us flat, right, Euclidean. All right, so looking at this equation, we basically can say, hey, we have pi r squared, we have circular internal rotation, and the structure of R happens to be split hyperbolic, so two-dimensional hyperbolic sign under split division, so 1/2 squared. And the external expression of this balance line, if you imagine the fluid action that's closing a loop, okay, imagine slow motion tracing how the fluid goes around and drawing a line in that path. Maybe you think of it as a spiral that goes around a torus, okay? So as you imagine that line, there's an exterior and an interior to that line, right? It doesn't need to be specifically the shape of a sphere now. You can have literally the surface of a torus. There's the inside of the torus and then the outside of the torus. And when you've divided the world interior and exterior, the exterior will always be the fluid action that's smoothed out of the interior. So that's why we have this E to some rotation, this phi naught, I'm calling it the perfect tempo 0, so the first perfect tempo in the fluid, okay? So, and that perfect tempo tells you how much external rotation represents the internal balancing rotation that we've got from hyperbolic split division. Okay, big mouthful, but if all of that happens to be set equal to only the derangements of the boundaries available in the fluid itself, which in this case is 5, then this equation, so you put a 5 in for n here, the number of boundaries, then exclamation point 5, if you remember, means derangements of 5. It's not the same thing as factorial, but it's related to the factorial function, okay? This equation is now entirely solvable. We can solve for our unknown, our 0 tempo, okay? As a little fun thing to look at, if complex number are in our division there and look at the real and complex of that balancing condition, this is what it is. This is what it represents, meaning it has two parts, real and complex, that are balanced factorizations among each other. So this is a complete set taken together that balances against itself. Oops, there. This way, okay. I'm going to go through these kind of fast because I know it's entirely new, but it is fairly simple, and this isn't any high-end math we're doing right here, right? This is just all the basic stuff. Hyperbolic signs, I think, are something familiar, or at least have been introduced to. In order to have this balance scale out and create something else, or if you want to talk a balance that can stand on the lower scale balance, then you would expect it to be the one that's caused by it. but it has to be caused by on the next scale out in which the next balance occurs, if it occurs, right? It's not a guarantee that this one will happen, but when you have the first balance, you can't form another balancing condition unless it happens to be compatible with the first balancing condition, because it was the first condition of persistence. So if you're going to have a property that persists, any property, by the way, that's very general, then by nature of its persistence alone, it's meeting the balance of the first boundary condition for sure. If it's meeting more, then the next boundary condition it meets is this one, okay? And it cascades up from there, but you always at least meet the minimum balancing condition of persistence. And then this second one. So this one is just going to be, of course, the inverse action of the action below. The action below is the hyperbolic sine, of course. But now, because we're going out, imagine a fluid, in order for a fluid to have balance anyway, as you go out in scale, there's always a twist. Okay, so here we're going out in scale. And so the inverse action, there's always a twist, which means the operations, instead of being squared in order to guarantee orthogonal arrangement, as they were on the first boundary, okay, we have an orthogonal arrangement by squaring things. And we have our hyperbolic sine as our action. So here we have our hyperbolic sine as our action twice again, but instead of being squared this time, our hyperbolic action is now on itself, right? And it's the inverse of this. So it's the reaction to the action below on the scale above after things have been twisted in operation and are now have to be considered on the next breaking scale. Had to be invertedly scaled because of the breaking scale on this next scale. So here we need to solve for B. We already know N is five boundaries, okay? And in order to solve for B, we just return back to our simple model for a quantum fluid. And in a quantum fluid, the highest resolution you can have, or the smallest scale you can meaningfully talk about, is the single quantum of the fluid, right? You can't talk about the properties of the fluid less than that because the fluid is quantized. Well, if you zoom out and make the next circle you can compose, but you can only compose it of circles of the same size, then the next circle out, the next resolution out, is composed of 6 exterior circles with 1 from the inside, which means it now contains 7. The first resolution had 1, the second resolution has 7, so our breaking scale symmetry is a scale of 7 to 1, right? All right, well, back up. That means now we can entirely solve this equation, and note it's the same sort of expression as we had in our first boundary, where we have an internal expression and an external averaged over expression being equal to some actual fixed number of hinges, I'm going to call them, but we'll just think of it as a whole number, okay, to start simple. Here, again, on the right-hand side, we have just 7 times 5. On the left-hand side, we can now solve for our perfect tempo sub 1, right? So our second tempo. Okay, well, let me move through a little faster here. Show the next 3 boundary conditions just look like this, by the way. Let's solve what this one means. Notice the thing to pay attention to is the n has moved to the left-hand side of the equation, and the 1/2, the thing it's being divided by is the Weierstrass constant, which basically, if you can't tell by or remember by looking here, it basically is the unit mix of a 1-dimensional thing with another 2-dimensional thing, where all of their actions are units. Okay, so it's a splitting condition, a perfect balancing splitting condition between 3 dimensions. Now on the left-hand side, we're saying basically we're taking all of our boundaries, we're splitting them by this perfect balancing split condition, but we're also we're writing that split, and we're putting it right at by the division of the breaking scale symmetry. So this is where the split is being put, but also this thing has to be wrapped back around on itself to close a loop. So it has to be singling out a pole. It has to be making a vortex of some sort, right? So you have to go around a torus, or you have to vortex. Or you have to carve out the rotational structure of a vortex in this balance. So this is just a geometric balancing of twisting 3 conditions together, which is really nice. If we move out, the 4th one is just a reflection, let's go back, of the first one. Notice pi sinh squared going on here, okay? Here's the 4th one. Now it's 2n, a double cover. It's an external expression that's now a double cover of pi cosine squared. Instead of the sinh squared, it's the cosine. So we switched from being hyperbolic to circular, and we switched from sine to cosine. Okay. Other than that, the argument is now also inverting the break and scale symmetry over the boundaries. All right. Simple equations, of course, each, but note that in each case we're giving ourselves a characterization of an external fluid action, right? The perfect tempo 0, 1, 2, and now 3. And if we move on to the next one, the fourth one. So we're getting 4 external actions, which you would consider if you're external to any of those. Those would be the action you encounter. All right. If you've been watching, you notice the fifth boundary here happens to close the symmetries of the first 4. Let's look at them all together so we can see that easier. Notice that if we draw a line to separate the top 3 from the bottom 2, then in the bottom section, everything is hyperbolically expressed. And in the top section, everything is, well, not everything, almost everything is now circularly expressed, but because of the duplication, we get another hyperbolic cosine up there too. So this would take probably about 4 hours to introduce in a comfortable way so that you can see the entire picture, unless you're already comfortable with these. So there might be a few people in the audience who are, and you can already see how these combine, but they geometrically combine as we go up in scale to close symmetries. So, you know, anyone want to save this screen or just follow our research online. Looking at this, that's worth looking into because it's really fun. But let's move on to why this gets exciting. Once we have that structure, okay, once we have these 5 balancing conditions in the fluid. So we just have a fluid, and now we need to make the balancing conditions because we don't have a box that we're putting in manually, right? It needs to be something that naturally occurs. Once that happens, we now want to address 5 really fundamental mysteries in physics, but I feel like it doesn't get enough attention, that we have found from observations so far that apparently there are 5 cutoffs in physical reality, cutoffs of measure. You cannot measure something, a measurement of time you can't take that's less than the Planck time. You can't get a measurement of length that's less than the Planck length. And you can't get a measurement of charge that's, well, you can't have more charge or more mass or more temperature than the Planck charge, mass, or Planck temperature associated with those length and time intervals. Okay, so this is really, it would be nice to start physics this way to students. I think they can handle it actually. But one thing you should notice is that all 5 of these are the fundamental dimensional descriptors of our reality. Seconds, meters, coulombs, oops, there's a typo there, kilograms and Kelvin. And so those dimensions, single dimensions, they're not combinations, by the way, are fundamentally interesting in our descriptor, but they are the base of our description currently, right? They are the reach that we mean to be independently definable. So we have 5 base measures in physics. There, there's the typo, the 1 kilogram. And these are the numbers, right? Now, the seconds, meters, coulombs, kilograms, Kelvin, this is a coherent system of units, right? They all coherently reference balance to each other. So they're in reference to each other already. They're defined in reference to each other. That's a really important point that I think most physicists aren't taught coming up, because we think of these as all random. And I think it's cool to think of any one of them as random. But when you have the entire set, the set speaks to itself, right? So the set is fixed, which means if you're using these units, these 5 dimensions of expressions, sure, you could convert that expression to something else, each one. We could convert meters to feet, right? But if we do that, we can't use our equations in physics without a weird correction factor in each case. This particular set of dimensions, second, meter, coulomb, kilogram, and Kelvin, allow us to interchangeably move between all of our expressions in physics of velocity and jerk and all the different kinds of expressions we can. We can move between them, and the only constants we have to stick to are the constants of nature. Okay, so this is a really important point. That's why we really like these dimensions, but it's also the only coherent system of units we have, right? There is no other coherent system of units. And what makes them coherent is that you can smoothly transfer between without having to always scale. Okay. Oh, and by the way, we want to explain these numbers, right? That's what we're going after here. So here's the big surprise. The 5 balancing conditions and their 5 external expressions all have double cover expressions of the hinges, of their hinges, that exactly define those 5 Planck constants. In each case, exactly in each case. So, yeah, I didn't put the exact numbers there. So if you go in and plug in, when we solve for boundary 1, for example, we find the value for this phi 0, this perfect tempo, the first perfect tempo balancing condition in the quantum fluid, right? And we then plug in down here in Planck time, we plug that number times by 2n, which is 10, base 10, okay? But it's base 10 because it's a double cover of our 5 boundaries. So externally you get a double cover, internally we get a double cover, right? We fold one action against the other action to make a balance. But externally of the balancing line, we get a split cover. Well, in order to then define the effect of the Planck, of this first balancing condition, we need to get its fluid action times by its double cover on the hinges, the total count of hinges it has. And that happens to be its right-hand expression. I didn't mention this, let's go ahead and do it. If you look at the number of, the numbers on the right-hand side here, it's starting from the bottom and moving up, we get 44, 35, 18, 8, and 32, okay? And notice the same numbers here, 44, 35, 18, 8, 32. The first 4 are negative, the top one's positive, it's external. The first 4 are internal on scale to us. But here, where those all those numbers come from, I want to make very, very clear right here. The first balancing condition gives us basically gives us exactly 44 hinges for its action. Okay, there's 44 points you could point to in the fluid in which there's twist about of that action, and the total collection of that twist gives this balancing condition. Zooming out, the cross section, so on the next scale out, we can cross all those boundaries and get now 7 times 5 of them, so it gives us 35. It takes up 35 of those hinges to do this, to get this balance. So 44 minus 35 gives us just 9 left, 3 squared, okay? I will pause for a second. It gives us 9 left. If we want to take those hinges and put them in balance, we need to square them, okay? So we take the 9 and put it as 3 by 3. But notice these hinges are now having a double cover external expression. So we square them, but we also have a twist this way and twist that way. That's how we're squaring. So we actually have 2 of them that are being invented because of it. All of the external expressions are exactly the same that way, except for the 3 gets phased. So the squaring now has a phase action on top of it. It can be at 0, 1, or -1. And here, that's how it plays out. So the charge boundary has a phasing of 0. The mass boundary has a phasing of -1, and the temperature boundary has a phasing of +1. Okay, now, why is that really exciting? Well, I hope it's really exciting already. If you've really looked into this before, there was not an explanation for these Planck constants. Okay, these were observationally, these were measured, and really they're measured in constants of nature and inferred because the constants of nature together imply them, right? To be technical. So there was no explanation for why. And here we said, we started out with a quantum fluid as our metric. And by defining the balancing conditions allowed from simplest up, we get a closed exchange of 5 balances allowed by that metric. These 5 balances happen to numerically exactly nail the 5 Planck constants. And that's exciting, not just because, wow, we're getting a mystery solved here, because it turns out that they directly relate to the constants of nature. How? Simply. The speed of light is defined exactly as the Planck length of the Planck time. Go type in the numbers for the Planck length and divide it by the Planck time, and you get the speed of light, which means the speed of light, being the limit of speed in the metric, is defined by the intersection of the first 2 boundary expressions. Literally the simplest 2 that exist, of time and space. Okay, and all of these, by the way, now we're gonna go a little bit in detail about the fine structure constant and elementary charge in later, so skip those 2 for now. But notice that in every case, the constants of nature happen to just be equal to the Planck expressions, okay? In some cases, you're gonna get pi. Well, let's just go look and see. We're gonna come back to the fine structure constant elementary charge in a minute. But say, look at the electric constant here. We got Planck time squared, Planck charge squared, divided by 4 pi, Planck length cube, and Planck mass. And that gives us the electric constant. In all of these cases, Stefan Boltzmann constant has a 60 because it was defined in minutes to seconds, but yeah, that's the only exception there. In all these cases, we only need the Planck constants and pi and G to get exact reproductions of the constants in nature that we needed to explain. Now, this is a really big deal because all of these constants, all the ones we listed in here, literally all of these need to be explained, okay? And what I'm telling you here is that we have a model here that cannot escape these as its actions so long as it's a quantum fluid, right? Right, now let's return to the fine structure constant and elementary charge. To get to that, we want to talk about the hyperbolic vortex equation. This is something that we've recently been working on and recently discovered, so it's new, and it's kind of the reason I wanted to get on here, to get some feedback from people to see how much they can connect with this. By vortex, by the way, we mean inside a fluid, a three-dimensional vortex. Think of a smoke ring. If you're blowing a smoke ring from a cigar or something, or if you're underwater, you can make one of these kinds of rings. So this is the sort of vortex we mean. It's a vortex ring that circles around itself with stability, okay? Now, in order to get that ring, we just want to write the equation for a hyperbola, which is be 1 over x plus x plus x cubed, right? And that hyperbola has to have, because of the x cubed term, at least 3 solutions. But we don't want a hyperbola that's just a 2-dimensional hyperbola. We want one that's then twisted under action in a full circle. So as you can see here on the left-hand side, we accomplish that just by putting one of them, the x cubed part. And instead of putting x here, I'm putting J as my variable. Okay, it's an acrylic. You can think of it as an x for now, but it's special because it characterizes this equation specifically. It's the variable for it. All right, so and it's the variable that has 4 solutions, right? So there's in this equation, there has to be at least 3, but when you look, there's actually 4. 2 of them are real and 2 of them are complex. I want to set this hyperbola, this specific hyperbola, we changed it. We taken a regular hyperbola and put it under 1-dimensional rotational full circle action, okay? And now we want to set this thing equal to its balance. What is its balance? Well, the fluid must rotate in 90 degrees this way at the same time that it rotates 90 degrees this way, if it's going to come around and close its loop simply, right? So the rotation angles, or the rotation velocities, have to be paired. They have to be matched up. And they're both, so 90 degrees this one or 90 degrees in the same time, you're going to get a sweep of negative pi over 2. By the way, I to the I is e to the negative pi over 2, if you forgot that. So you can geometrically very easily represent this as just a rotation and a rotation, 2 perpendicular rotations at the same time by the same sweep angle, okay? That's what our vortex needs to be. And it needs to be rotations that swing around some boundary, some 0 point, some pinch-off point, okay? And in this case, we're gonna label that Planck mass, or MP, because it's the answer, because it's our 0. It's the place where discreteness in the fluid becomes a 0 pinch-off point. Everything outside that scale treats the fluid that we're talking about as being completely continuous. It has a continuum action. Everything inside that scale is discontinuous. So this is our boundary of discontinuity, because these actions are rotating within the degrees of freedom internally, okay? I know it's a lot, the first time probably seen it, unless you've been watching our stuff or keeping up with this. But this equation, when you put in the Planck mass that we've measured, and we can define it in terms of a gamma function, we'll do that at the end. But just right now, we know the Planck mass, throw it in there, okay? And by the way, because it's times 10 to the negative 8, you could ignore it, and it wouldn't change your output, your solutions for this up until the 8 significant digits, okay? So we get the first 8 right. However, you can get the next 1, 2, 3, 4, 5, 6, 7, 8 here right also by putting that in there. And what do I mean by right? Here's the solutions. So you just plug this into Wolfram alpha, for example, the equation up top, and you kick out 4 solutions. 2 are real, and 2 are complex. By complex, remember, that means it's made up of a real component and an imaginary perpendicular component. We put an I on it, okay? Now, interesting things about those solutions is that if you take all four of them and add them together, they balance out to 0. Beautiful. Of course, we would have expected that, I think, because we were trying to make a vortex that balanced. That was what we defined, right? But if we take the squares of those solutions first and then add them together, and then add them together, we get -4 pi, the number that characteristically describes a spinner. Okay, and if you recall, spinners are, of course, like electrons. If we take the 4th power of each solution first and add them together, we get -8 pi plus 48 of the Riemann zeta folds and doubles. It's a Riemann zeta doublings. Now you can define that in terms of pi. You can do lots of ways, but look, there's hinges basically going on here related to 8 pi revolution. Okay, this is really interesting balancing conditions of our equation here. But what's more interesting or more exciting, I think, well, let's skip this one. That might be too in depth. I'll come back to it maybe later. Is that this fine structure constant, the number we wanted to explain to all those digits, happens to be the square of our first solution to the vortex equation, to the hyperbolic vortex equation. And by B, this is what the accuracy I mean. 0.072973525, and then instead of 698 with an error of 24, it's 729. Now notice the error bars, sigma 1, 9, 8, that gets us up to a 22, right? So we're another 7 off. So this is almost within 1 sigma of our exact best measurement. And I wasn't going to put this in this talk, actually. Well, maybe I should. Yeah, I'll get to it. And if you don't square it and you times it by the charge boundary, the only cutoff boundary of charge in the fluid, right, the Planck charge, then you get the electron charge. So the vortex equation, the first solution of the hyperbolic vortex equation, takes the charge boundary and wraps it into the electron. I hope that sounds really exciting because it's visual and visceral, but that should also, okay, so the first solution of vortex is characterizing the electron, right? We've nailed, and by nailed, I mean it got the constant of nature, we call the electron charge, to all of its significant digits. So this thing's characterizing the geometry of the fluid on these scales between the Planck mass boundary and the Planck charge boundary, and it's characterizing how they're being twisted into balance. Okay, make you really interested, of course, in the other solutions, maybe, right? Remember, there were 4 solutions to this hyperbolic vortex equation. And the first solution gives us the electron charge. Precisely, it gives us the fine structure constant exactly and the electron charge. There's a lot that goes with that, of course, because once we know those, we get the Bohr radius, we get all the structure of the atom, anything to do with the electron's charge, basically, in radii. Okay, that's a really big deal. And now to go into what else this parses for us, this is meaning that in order to get a balance in our fluid, our 5 different balancing conditions, we have an internal structure that's different from an external structure in that balance. The internal structure has 3 actions that fold, right? 3 levels of 2 actions that fold, I should say. And then the external expression just has its regular expression, its double crossing expression, and its last closing expression. So these fluid actions, if you just imagine waves going around and crossing through each other and need to balance, you can imagine the trail of the wave that needs to close on some external boundary, and it needs to be circular, right? That total sum of waves need to have a circular closing boundary. The inside of that boundary, by the way, is going to be characterized by the figure 8 knot, the hyperbolic figure 8 knot, because this is the simplest knot to form fluidly, right? The very simplest one for nature to even do, but also because this figure 8 knot is defined as the dilogarithm. Okay, well, you can see the equation right here. It's a double cover of the Gliese constant. Okay, it's a double cover expression to begin with. It's the simplest and most reduced volume for any of these expressions. And its internal structure, notice, has a -1 to the 2/3 power and a -1 to the 1/3 power. Its power structure of the dilogarithm, the way it's twisting about itself, or think of its helix structure, is -1 to the 2/3 and a -1 to the 1/3, right, in dilogarithmic argument. All right, that's exactly, of course, what we get in the internal structure of the charge pattern for nature, right? And the external structure, if you think of charge in terms of fluid flow, if you have a domain of restricted boundary, so think of a sphere. If the sphere is defined as fluid flow, as a region, as a boundary where no fluid flows out or in from that boundary. If there's any fluid flow on the boundary, it stays on the boundary, okay? If you define fluid flow that way on some region, or if there is any region that has that kind of fluid flow, then that flow, that boundary exhibits zero charge. Charge is the expression fluidly going out, in, out, in, out, in, like a wave action that's going, is pushing itself further out into existence than collapsing and back and forth, okay? That's the charge expression. There are exactly 3 intersections where there cannot be charge in this model in order for the balance to happen, right? So I already mentioned there's a balancing condition. Well, that balancing condition gives us that boundary, that sphere, that the inside is built with the figure 8 hyperbolic knot, the fluid action and its complement. But the sphere itself, the whole collection of that knot and complement, has a boundary condition that's 2-dimensionally restricted, okay? And that boundary is where the first one here, on the red one, the 3 in the bottom, represents the charge of the neutrinos. 3-dimensional direction from that boundary, there's zero charge in all 3 directions, right? Well, as we go up, we get to the inversion scale of 1, and then the upper boundary of the universe. And the inversion scale gives us a 0 too, because of course at the inversion scale, so this is the neutron, you can't have up and down. You pinched everything out to 0. And of course at the upper outer boundary, it goes to 0 boundary condition too for balance and symmetry. All right, so what we're saying is that the structure of our 5 Planck constants, the structure of the 5 balancing conditions that self-close when you take them all together, cuts the world off in terms of charge. And I really should point out here that what we mean by charge and what we mean by the scale of these numbers, 1 or -1 represents the electron charge, right? So this is in the scale of the electron charge, or in other words, it's in scale of G1 times the Planck charge, okay? So that's our scaling for these numbers. All of these are referencing internal versus external expressions of that charge boundary when we fold it up to form the electron. Literally, all of them are implied by this exact same fold. We don't have to refold. These are just the different repeating intersections of the fold we've already made in our hyperbolic vortex equation. All right, now for something that is super, super exciting. As I told you before, the Coyote equation is the only equation that, let's skip right back up to it real quick. The only equation that purports or has attempted so far to make sense of or pattern in any way the masses of any of the particles. Now, it only does it for 3 of them, right? People have tried to extend this to others, and it doesn't work so clearly, but it's still been considered kind of interesting. But this is the only pattern. This is the only one that's given us something interesting, right? It gave us a geometric expression right in the middle. What exactly that means, there's a lot to go into and guess there, but there's a hint here. It's the only hint we've had. So I want to go now and show you, with that in mind, keeping in mind that nobody else has had a pattern besides Coyote for the masses that matched. And by the way, the matches are extremely easy to identify. It's extremely difficult to find a pattern, but it's really easy to verify a pattern, right? For example, I can put up this pattern here, and you can take a screenshot, and you can go verify for yourself that all of these numbers perfectly work out. Meaning, we have the list of, where did I list these constants? We have, these are the matchup between that expression and measurement, right? So measurement's in the bottom with the parentheses in each one. And these set of equations I set right here match all of those numbers, the masses of these particles, perfectly to every significant digit. Now, these are some of these numbers, like the neutron, proton, electron mass, are numbers that we know, they're like the best significant digit numbers we know in all of science, right? We've measured them to 12 significant digits. It's extremely, extremely accurate. So let's look at this pattern real quick. Let's make sense of it. But first, let's note how simple it is. In fact, let's make it a little simpler. The pattern on, or the extension on the right, the 1 plus the limiting Gs squared, that's just a reflection term, okay? So it's also a very, 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 very small term because it's a reflection term. It's a next order contribution. So it doesn't even show up to like digit 7. So I'm going to just ignore it for now. But if you want to get an exact prediction for everything, remember this one needs to be in there. Okay, but that's just the next reflection. So I'm going to cut it off and explain this pattern now. Notice first thing, it's an extremely simple pattern. Now we've been wanting a pattern for matter particles since we knew they existed, right? Since we've measured their masses, try to explain them. In order to explain the masses, first step is to pattern them. But notice what happens when we did. When we find a pattern, it breaks up naturally into 2 groups. First of all, the structure of every line is basically the same. We have the subtraction of 2 masses on the left side, equaling the mass of something on the right-hand side. But on the right-hand side, there's always a either a phase adjustment or a doubling, right? A squaring, a folding, let's call it. And there's always this combination of 3 different terms, 3 different geometric representers, right? Pi, you might guess, represents a circle. 3, you might guess, represents the limit of a hyperbola. If it's 1 over x plus x cubed, represents a hyperbola. Then between 0 and 1, if you let it go to x equals 1, our limit becomes just 3, right? But mu, what is mu? That might be less familiar. Let's do that right in my hair. Oh, I didn't. The logarithmic integral, looking at these 3. The logarithmic integral of x. So if you put li parentheses x close parentheses in Wolfram alpha, for example, and then say equals 0. Okay, the logarithmic integral has it goes through a trivial 0 at 0, 0, and then dips way down, and then comes back up and crosses through 0 again. And so that it has one non-trivial 0. All right, so that non-trivial 0 is this mu, this number, and it represents basically 0 plus mu. But I don't have to put the 0 because it doesn't change our math here, right? But think of this as 0 plus mu, meaning this is a characterization of both of the boundaries of this logarithmic integral. What is that representing? Both walls and the inside of the vortex. So a vortex needs to make a limit where it stretches a gap, right? It pushes this way and that way. And so it's going to hold a 0 and a false 0, you might call it. It's going to hold another 0 boundary. Well, what other 0 would be better naturally than the logarithmic 0, right? Both of the logarithmic zeros to hold this balance. So we're saying, why logarithmic? Well, because we've defined all of our balances here to be exchanged between hyperbolic and circular, right? Under exponential balance. So this condition here, all we have to do, if you ignore the squared on the first equation on the left, the only difference between all 3 of these would be the phase adjustment. So this 2 to the 0 can swing to +1 and -1 to give us our different expressions. But when it does, when it swings to the +1, it goes from 2 to the 0, which is 1, to 2. It doubles. And when it goes from the 2 to the 0 to 2 to the -1, it halves, right? So this swinging is an act of doubling and halving, kind of the thing that happens when you do split division, right? If you take something and break it in half, you've always, by definition, also doubled something else, right? So I have one piece, one stick, and then I had 2 sticks, right? So, and I had one stick of a certain length, and now 2 sticks of half that length. So it means, it's a perfect balance to have halving and doubling together. But notice when we get to halving, that line also gets, the one you cut in half, 2 copies, is squares. Okay, sounds very reminiscent of our first balancing condition. I don't know if you picked up on that yet, but here's the, I apologize for the difference in font here. I just threw this together yesterday. The second set of conditions. So we have our full set here, right? The red ones we talked about here. It's a phase adjustment, and there's 3 things happening: a doubling, a halving, and a squaring in that construction. And the bottom, though, the bottom 3, you can ignore the coloring, the yellow and green. That was for some other talk I was giving. The bottom, there we go. They don't have a phase adjustment. They have a fold and a further fold and a further fold. Think of it as a crossing, a simple crossing, a more complex crossing, and then the final, a square crossing and a 4th crossing, right? All of these, though, represent basic geometric collections, so a balance between the logarithmic zeros, a hyperbola, and a circle under phase operation, or under 0 phase operation, gives us the difference, gives us the projection of the neutron and the proton and the electron, but the difference between the neutron and proton has to be multiplied by 3, because we're doing this in 3 dimensions. All right, that's really simple. That's really beautiful. And all we have to do to get the other the other half of particles is to show that the internal construction, instead of having these crossings, what we're doing instead is folding. So we're taking the same balance in the folding. But notice there's a hidden exact structure in here. If you start from the middle line of blue and go from the 2 to the 2, 2, so think of it as 2 to the 4. Moving upwards, we go to 2 to the 2, and moving downwards, we go 2 to the 2 to the 2 to the 2, right? So that 4 goes up to 16 if we go down, and it goes down to 2 if we go up. That's a squaring and a halving. And then if we look over at the 2 for the mass of the strange particle, it's doubled. So the bottom one also contains a doubling, a halving, and a squaring. And in this case, the doubling and the halving belong to the same line. And orthogonal to that, the halving and the squaring are together. Notice in the top line, the halving and the squaring are together at 90 degrees to that, right? The whole top line keeps the halving and the squaring in the top line. And down below, the halving and squaring jumps us from the middle line to, sorry, the middle blue line to the top blue line and the bottom blue line, right? So that's its line of action. So hopefully you can kind of see that this is geometric orthogonal arrangements between all of these that are either phase adjusted and counter to the phase adjusted, by the way, it's the same thing. If you look at the back end of the phase adjustment on the inside, you get these different constructions. Okay, we find this extremely interesting. By the way, this is entirely new. This is the reason it's interesting and exciting though. The numbers line up extremely accurately. I mean, just look at these, look at the neutron one, right? It goes all the way out to the error bars, but it lands the error bars. It's in the error bar. All of them are in the error bars. Now, you might note and say, okay, well, before I say that, the proton, the neutron, the electron, we know extremely well, but it turns out that if you divide the neutron by the electron, we know that a little better. And if you divide the proton mass by the electron mass, we know it better too, by one more digit, right? And we still get those right too in this geometric expression. So that's fantastic. Exciting, but why it's exciting is because it's trying to tell us a geometric structure, a structural picture of what's going on. It's literally just giving us a balancing condition of the hyperbolic vortex under 2 phase operations and internally under how the crosses, how the wave actions cross differently with those different phases, right? So it's an extremely simple picture, but there have been no pictures available before. So this is the first proposal I'm aware of in history that actually nails the constants, the masses of the fundamental matter particles, but it nails them all, right? The KD equation did nail in relation 3. This one nails all of them in pattern. And there was something else I really wanted to say about this. Oh, maybe I'll have to come back to it. Okay, and that was by generation. We have another pattern that if you treat the split hyperbolic action just perpendicularly, then we have to look at the cross section now of the actual vortex equation. The vortex equation, remember, had 2 solutions. This is where it gets really, well, okay, it's been really exciting for me, but this adds another level of excitement. Remember, the vortex equation had 2 solutions, and the first solution characterized for us the electron charge. So it, in general, now describes the electron, but the equation itself reached to the mass boundary, right? The vortex equation is also connected to the mass boundary. So if you take the second solution and the first solution together, you would look for a relationship between the electron and now something else. And it turns out that the other thing that fits this pattern, the thing that crosses the vortex balance, gives us intersection for the mass of the electron, which we already know before, but this is in terms of mass, by the way, not charge this time, but also the mass of the proton. Oh, I remember what I was going to say about the last one. Notice this, this electron, proton. Never mind, I just forgot it again. Yeah, okay. Oh yeah, so what we're saying here is that before we had an explanation that gave us all the constants of nature from the 5 balancing conditions, including, and then when we threw in the hyperbolic vortex equation, we get the fine structure constant, which then gives us the electron charge. So now all the constants in nature except for the matter particles, right? There's some constants in nature that have the mass of the electron, mass of the proton, so on in it. Now, though, we're nailing all the matter particles, which then give us the rest of those other constants, and more fundamentally, the matter constants themselves, the mass constants. Okay, notice how fundamentally in this pattern here, the central action is just a cross between the first two vortex actions, balanced squarely, right? Je 2 over je 1 squared. And on the right-hand side, we're saying that equals to, think of 2/3 as representing a torus under square action, because it's square now. But the alpha Feigenbaum constant explains, it's a universal geometric constant that explains how things tine, so how they split. Think of a tuning fork or a tree, a branch that's growing and then splits and then splits and splits. So in natural bifurcation, the alpha Feigenbaum constant characterizes the way that this splits, okay? So if you put -1, you've now put the splitting under hyperbolic balance, also because it's squared. So it's you're hyperbolically splitting under balance, under square balance, the vortex equation, okay? And getting from that a return of the mass electron and the mass of the proton. This is so central and fundamental, but when you zoom, I'm gonna switch the bottom ones for now. I want you to see the structure here, that below all we have in all of the internal structure, all internal particles, is just, again, the alpha Feigenbaum -1 component to a power of 0 or 2, and a 2/3 to either a 1 power, a 3rd power, or halfway between to the 3rd power, right? So there's a very simple, do I have all put together? No, I don't. Okay. There's a very simple action going on between all the matter particles here in this orthogonal action to the vortex equation, or when we put it in vortex square arrangement, when we talk about these things geometrically in vortex square arrangement, they perfectly phase to give us the mass of the electron and the proton as the crosses that balance that geometric arrangement. When we go out of phase and we flip it, put a square root of 3/2, or we flip it the other way, square root of 3/2 above and below, then we get characters. Well, just look at the powers. We have -1, 2, and -e to the 2 gamma. The gamma is the Euler-Mascheroni constant. This is a constant that we are coming to interpret as, and we're really interested to see what other people think about that. The Euler-Mascheroni constant apparently in this structure gives an internal wrapping measure, right? So this entire thing makes a spinor structure, doubles it, and wraps a closed system. And internally, that's the effect, right? This is the external effect. That's the internal effect of the crossings. All right, I know that's a lot, that's really fast, but notice here, another perfect lineup in mathematical equations. This one, oh, go back to, yeah, these guys here. A thing to notice about this equation, about this setup, let's make it more pretty. It's non-dimensional. Does that make sense? So if you look at, say, the neutron minus the proton, those are both in mass, in units of, say, kilograms. So kilograms minus kilograms is a measure of kilograms. And on the right-hand side, we have kilograms. So we can divide it out and get so that there's just no units at all, right? Kilograms over kilograms, it goes away. This expression is this pattern geometrically expresses the scale foldings between these things without giving us the scale itself. Does that make sense? It's a geometric pattern that's inherently implied without even having to nail the scale. It's inherently there. The downside, you might say, of that is that it can't give you, say, the mass of the proton unless you have the mass of the neutron and the mass of the electron, right? You have to know 2 of any of the 3 in order to kick out the 3rd. So that was the thing I'd forgotten to mention before, which makes it so here, we're really interested in the lineup, but because we have a perpendicular arrangement, expression of the masses also, 2 equally true, and they tell the same story beautifully, expressions of mass, this allows us to now get a perfect lineup in 2 independent directions and nail down the exact masses. So here's also the alignment in the family, right? In these numbers here, we get this kind of matchup, which is fantastic. And which time do we have? It's basically time. So I'm going to take like 2 more minutes just to show you some extra cool things, and then we'll take questions. This is one thing that I really want to, if you take the 5 external flow actions that we solve for in the 5 boundary conditions and add them together. So n is 5 here. So add all 5 together. That's what the sum of this, that's what this symbol means, okay? So we add all 5 expressions and we take the gamma of them. Now, the gamma is the factorization, how they factor. So this equation basically says, on what boundary, that's our question mark, at what scale, you could say, do the 5 rotations factor with perfect balance? What do I mean by perfect balance? Well, since we're using the gamma equation as the factorization equation, then I want to know on what scale does, however this is factoring among these 5 rotations, I want it to be equal to the way things inverse factor, right? So we just make it equal to the infinite integral from 0 to infinity of 1 over gamma. Okay, that's a constant. It's an integral, but it gives you a constant. And this singles out a single boundary on which this condition is true. So, say it again in English a little slower. This equation right here is asking, on what boundary do we get a perfect factorization balance from the 5 rotations of our fluid, okay? And when we solve, it turns out it is exactly the Planck mass boundary. I hope this blows somebody's mind here. If you've worked with the gamma equation before, this is a fundamental gamma expression of balance that nails a condition in physics, okay? I mean, all of these things have been doing that, the concentration and so on, but this is an entirely independent way of coming at it, and it did the same thing, which should, of course, make you excited to look, well, if this is a expression for how those 5 boundaries factor, then shouldn't they also, hint from our vortex equation, squarely factor and to the 4th power factor? And it turns out that if you search for the boundaries in which those are true, and by the way, the numbers here, it's pulling out the number and the power, not just the number or the power, right? It's nailing it entirely in scale and value. This whole set also follows. So it's perfectly balanced. It's simply squared. Yeah, did I say that? Oh, yeah, right here. It's primitively balanced, it's elliptically balanced, and it's figure 8 hyperbolically balanced from its factorization, its primitive factorization, its square factorization, and its 4th factorization. Okay, this is a lot, and that's a lot of math to go into, but let's show some pictures here. If we try to graph on Wolfram alpha the balancing conditions we've been talking about, or the union of them, these are some of the conditions we get, the real or imaginary component. So you can see the factorizations here, how beautiful symmetric they are. But they lead to some very interesting patterns on specific scales here that are really fun to talk about. So, okay, this is a real crash course to the concept we've been working on over the last 20 years. And let me escape now so we can try to take some questions.
So thank you, sir, for your wonderful lecture. And it is really an interesting and exciting lecture. And I think students have enjoyed it lots and learned a lot of things. So now if you allow us, we can start our discussion. We have got some questions. So I can read the first question. I can add it in our screen. You can also see. So does the equation mean that we can describe every physical constant by some rotation, as you have described by the vortex equation? And what does the vortex actually means here?
Yeah, so yes, all the constants of nature, the ones we call constants of nature in physics, are nailed down already by this. So we've already published this out in the book and so on and everything, but I'm not claiming that I think it should. I'm saying that this is already characterized and the math already lines up. So yes, all the constants of nature are described and can be described in terms of this very simply and very beautifully. We don't need any weird factors out in front, right? What does vortex actually mean here? In short, by vortex, I mean a fluid action that wraps back around on itself. But the one that's doing this it's really Mobius vortex action, because when it wraps around and comes around to where it looks like it started, it's out of phase now. It's exactly backwards. So it goes around twice before it looks exactly the same. But this is because it's 3D. Well, it's really easy to see with that. In general, vortex just means a balancing condition that wraps under simplest balancing conditions possible. Okay, and I showed a picture basically of like a dolphin ring of a vortex, but it literally takes that sort of structure. So it divides the fluid in a fast round or a small ring, right? It has two different rings of action that it's dividing the fluid in, but it divides it in the same way that, say, the dolphin ring did. It doesn't disrupt everything. It twists things around it and leaves the exchange as it goes out. Yeah.
So thank you, sir. We have another question from him. What is your view about the mass hierarchy problem in standard model in terms of your vortex parameter?
So the hierarchy problem represents in general for everybody a question about why are these huge scalings, right? In general, in the mass hierarchy problem, why are there three different families? Why are there three different generations and so on? How do we describe them? In this model, we didn't. Let me back up. In this model, we started out just assuming we had a fluid and we put it under balance. We defined the vortex equation and then asked, what are the intersections of that balance that we've made, right? We got the square one, we got the fourth one, we got the zero one, or the simple one gives us a zero, right? Those, I forgot what his question was, he just took it off. Mass argument, thank you. Those different exchanges automatically nailed all the values. So the mass hierarchy problem is automatically explained as just being the return exchanges of the different scales of this expression. By the way, I should also mention that the hyperbolic vortex equation, as it kicks out as its first solution, squared being the fine structure constant, it's also a scale-dependent value, right? If you don't scale it all the way to the limit down to the Planck mass, then you get a different measure. In fact, the other limit is to put in 1 instead of the Planck mass. So in the hyperbolic equation, let's go to sharing here.
So
in this one right here, if instead of the Planck mass, we put 1 as your boundary, that's the other limit extreme you could, then you get a scale of how much this thing has affected the metric all the way out to there, okay? And that makes sense. So if a vortex is distorting the fluid, if you're near the vortex, you're going to get maximum distortion, but you're not going to characterize at that stage near it the total distortion that the vortex is creating. Why? Because some of the distortion's past you, right? Some that's beyond your scale. If you zoom out, then the local effect of the distortion to you decreases, but the measure of the total distortion you now think that the fluid has increases, but that tapers off as you go out in scale. So that's exactly what this equation does as you taper that off. And by the way, we have measurements of how the fine structure constant has changed over time, and we've only measured so far, but that measurement is very suggestive of what the possible range would be. And if you put in a 1 here versus the Planck mass, those two ranges really suggest, well, the one range exactly matches, the other one really suggestively points out our first data point. So
thank you, sir. We have another question. So does your equation have any connection with supersymmetry?
Good question. So supersymmetry, I assume you mean in the in superstring theory or M theory sense. It predicts that there's going to be repeat particles of the matter, right? This one, it's supersymmetric, but Mobius supersymmetric. So it folds that symmetry into itself. So the only supersymmetries it gets is the square crossing and the fourth crossing. So in a way, I want to say no, because in the traditional way that string theory suggests for supersymmetry is the prediction that there will be other supersymmetric particles of greater masses and so on. That's their prediction. This one says that there won't be. So in that sense, it's completely different. And so if we find a single supersymmetric particle, then this model is not characterizing things correctly, right? But also very interestingly, this model also says that there will not be any other particles. This is a closed set. It nails them all. If there are any others, it screws the entire pattern up. It makes it so there's not a balance. So because we need a balance, this also says that there are no more, which great prediction. If you find one more of any kind, then we've got a problem, right? So, but however, at this point, until we find a particle that we haven't found before, until that happens, it's really exciting to note that we now have one simple geometric explanation to connect all of these, and it does it mathematically. I would expect some people to kind of be kind of confused or worried about the fact that these numbers popped out so well when they were in meters, seconds, coulombs, Kelvin, and all that stuff, right? But let's see what the next question is and see if someone has a problem with that.
Yeah, this is maybe the last question. So, do you have any plan to establish a new code system based on the constant?
Do you mean code system in physics, or do you mean code system in computer?
No, maybe. So he maybe want to know about. So, do you planning to make any code to calculate this constant?
Oh, well, yes, yeah. I've already got it online. So I've got an entire 3-hour lecture of this online that shows you all the math in much more detail than what we did, right? And you can pause it and go verify on Wolfram Alpha and so on to catch up with all this. But yeah, the predictions are all there, and it's really easy to verify yourself. So, and you should not take something like this under anyone else's assumptions. In fact, just don't repeat anything like this until you've checked it yourself. That's how it should go, right? Yeah.
So thank you, sir. So can we get any idea of spin from your model?
Yes. Yeah. Of course. So spin 1/2. All these things have spin 1/2 because as they're twisting around, the vortex is Mobius inverted. So it has to go around twice in order to become back to what it was. That's just what it's characterized. Yes. So and that's a really good question, by the way, because spin has not been, at least in my traditional introduction to physics, spin was a real big mystery. When I wanted to explain it at first, I'm like, okay, so you're saying that there's something down at the electron that's twisting around. It's, no, nothing's spinning. Why do you call it spin? Well, it turns out that we do call it spin because it has all the effects of something that's spinning, but we define the electron as being 0 size, so you can't say 0 is spinning, right? So it's a confusion in action. In this one, we don't have a 0. We very clearly, there are no zeros, first of all, in the entire model because the fluid has at minimum pieces, right? That's the smallest contribution you can have. But the smallest balancing condition, the smallest persistent action that can exist requires that first balancing condition of time. So that's literally the smallest thing that can exist, and that's 10 to the negative 44, right? And so on. So yeah, now I'm lost track entirely what the question was, but cool.
Yeah. So thank you, sir. As we don't have any questions, so we should conclude our discussion session.
Cool.
So thank you, and I'd like to say thanks again on the behalf of the Department of Physics, Pabna University of Science and Technology. It is a very exciting lecture, and it is very great webinar with you. And I think students have learned a lot of things. So we actually very grateful to you. And as you know, you are too busy with your works, with your theoretical works, and
so if anyone wants to join
with your webinar also.
If anyone wants to join our research team or just catch up to what our research team has been doing, you can go to the Vortex Institute, right? You can also read one of my books. The last one was Perfect Universe. You can see that, right?
Yeah. You can see.
Or start out with Einstein's Intuition. It's a much bigger book, but very, very well received.
Okay. So hopefully we'll arrange another webinar with you in near future.
All right.
And thanks for everything. And
thank you.
Bye for today, and good night.
Good night.
Bye.
Bye.